1, 1, 2. Now let's say we're told the surface fxyz equals 0, which we considered before, intersects this surface orthogonally at the point -1, -1, 2. We're asked to find the values of d and d. Remember, of course, what f and its gradient vector are. Now, in order for these two surfaces to intersect orthogonally at this point, we must find this point lies on both surfaces and that these surfaces are orthogonal at that point, which means their normal vectors, which are their gradient vectors evaluated at that point, should be orthogonal. So first let's check they intersect. Now it's clear if I put this point into our equation for f, that equation is satisfied. So we can see that f minus 1 minus 1, 2 gives me 3 times minus 1 squared plus 2 times minus 1 squared plus 2 squared, which is giving me 9. So minus 9, which gives me 0, so it's certainly on that surface. If I look at the other surface, I can see that I have minus 3 times minus 1 squared plus d times minus 1 squared plus e times 2 squared equals 4. So I've got minus 3 plus d plus 4e equals 4. And so, in order for this point to lie on this surface, I'm going to need to make sure the equation d plus 4e equals 7 is satisfied. So, as long as this equation is satisfied, the point does indeed lie on both surfaces. In order to see whether they intersect orthogonally, we need to look at the gradient vectors. Now, in this case, we can see that at the point the gradient of f is given by minus 6, minus 4, 4. To find the gradient of the other surface, we need to think about the function h, which is given by this, and we're of course looking at the surface which we get from setting this function equal to 4. In this case we can see the gradient of this function hx, hy, hz is going to be minus 6x 2dy 2ez, and so at the point this gives us a gradient of 6 minus 2d 4e. For these to be orthogonal, we need their dot product to equal 0. So this means we need minus 6 minus 4, 4 dot 6 minus 2d 4e equals 0. So this gives us the equation minus 36 plus 8d plus 16e equals 0. And if we tidy this up, this gives us, dividing through by 4, 2d plus 4e is equal to 9. So this is the second equation d and e need to satisfy in order to have orthogonal intersection. The point clearly satisfies this, it will satisfy this as well to give us a point of intersection. We have this equation, and for them to be orthogonal we also need to satisfy this equation. So to find d and e, all we need to do is solve these equations. So multiplying this equation by 2, say, we can see we have this. Leaving this as it is, we have 2d plus 4e equals 9. If we subtract, we get 4e is equal to 5, so therefore E must be 5 over 4. If E is 5 over 4, this equation then tells me D is equal to 7 minus 4E. 4E is just 5, so this gives me 7 minus 5, so therefore D is equal to 2. So as long as E is equal to 5/4 and D is equal to 2, we have an orthogonal point of intersection. So let's say we're now asked to calculate the value of the directional derivative of f in the direction given by 1, 2, 2 at the point minus 1, minus 1, 2. As we've seen before, we need the directional derivative at this point, so we can see at the point the directional derivative is given by minus 6, minus 4, 4. And to find the directional derivative of f in this direction, 1, 2, 2, the direction is, let's call it u, and to work everything out we need a unit vector u hat in this direction. So normalizing, we can see the magnitude of this vector is 4 plus 4 plus 1, so that's 9 square rooted, so the norm of this is 3, so we need 1 over 3, 1, 2, 2. So let's make that clear. So now we have the value of the gradient vector at the point and a unit vector in the direction we're interested in. We know the directional derivative, which we call f subscript u at this point, is just our unit vector dot producted with a gradient vector at this point. So this is going to be 1 over 3, 1, 2, 2, dot producted with minus 6, minus 4, 4, and this will give us 1/3 of minus 6, minus 8, plus 8. The 8's cancel, so I get minus 6 over 3, which is minus 2. And we should notice that this tells us the rate of change of f at this point in the direction of the vector 1, 2, 2. In particular, because this rate of change is negative, the function is decreasing in this direction. Okay then, for our last example, let's write down the direction and rate of maximum increase of f at the point minus 1, minus 1, 2. As you should know from the subject guide, if we evaluate the gradient vector at the point, this gives us the direction of maximum increase. The rate of maximum increase is then just the length of this vector, so it's the norm down to f, which will be the square root of 36 plus 16 plus 16, which is going to give us the square root of 68. And that really is that simple. Bear in mind that if we wanted the direction of maximum decrease, it would now be minus the gradient of f, and the rate of maximum decrease is minus all this stuff.